Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is binary tree to BST. First of all, let us start by understanding the question. What does question say? It says that given a binary tree, convert it into binary search tree in such a way that keeps the original structure of the binary tree intact. So basically what it's saying is that suppose we are given a binary tree. What is a binary tree? It means that for all the nodes it can have maximum 2 children. That is what is a binary tree. So this is a binary tree. Now we want to convert it into a binary search tree. What is a binary search tree? For a binary search tree, first of all, it is a binary tree. So binary search tree also holds the conditions for a binary tree. And in binary search tree, for all the nodes in the left subtree of that node holds less value than that particular node. So for example, suppose the value here is 10, okay, then the nodes in the left subtree of this node should hold the value less than 10, okay. So suppose this could be 9, then here this could be 8, and so on. And the values on the right hand side of that node on the right subtree should be greater than that value. So on the right hand side we should have values greater than 10. So for example, let's have 15, then 18. Now on the left side of this, what can be the value here? See, this is on the left side of 15. Now this condition should hold true for all the nodes in binary search tree, okay. So left child value should be less than that node's value, should be less than parent's value, and the right child value should be greater than parent's value, okay. So for 15, this value should be less than 15, but this node is on the right hand side of 10, okay. This whole subtree is on the right hand side of 10, so this value should be less than 15, but it should be greater than 10 because this node is in the right subtree of 10. So all the nodes in this right subtree should have value greater than 10, but less than 15 for this node because it is on the left side of 15, so it can have something like 13, okay. So this is basically binary search tree. So now what it is said that we are given a binary tree and we want to convert it into binary search tree, but the structure should remain the same. So this structure should remain the same, okay. Now place the values, rearrange the values such that it holds the property of binary search tree. So what can be done? We can place 6 here because there is no right hand side, so this will hold the largest value. Now these 3 values will be less than 6, therefore 3 and 1. The next largest value will be here because this value would be less than 6, this value would be greater than this. So I think 4 will come here, then 3 should come here, and 1 should come here. So all the values in the left subtree of 6 are less than 6. 4 is greater than 3, that's why it is on the right hand side of 3, but it is less than 6, it is on the left side of 6. 4 is in the left subtree of 6, and 1 is the smallest, it is on the left side of 3 as well, okay. So this holds the property of binary search tree and the structure remains the same. Now we can also form a binary search tree like this: 6, 4, 3, 1. This is also binary search tree. This also holds the property of binary search tree, but the structure does not remain the same. So we want to keep the structure same and the values which can have a different combination, okay, such that it follows the property of binary search tree. So this is not valid, this is valid. Now let's read further. So if we look at the example 1, 2 and 3, this is a binary tree given. We want to convert it into binary search tree. Is it a binary search tree? No, because 2 is greater than 1, still it is on the left child, okay, of 1. So this does not hold true. After getting converted to BST, it will look like this: 3 is greater than 2, 1 is less than 2, okay. So it is on the left hand side, this is on the right hand side, okay. Structure remains the same. Then if we look here, 1, 2, 3 and 4. Now 4 is greater than 2, still it is on the left child of 2. So this is not binary search tree. After getting converted, it would look something like this: 3 would be at the top, 4 would be the right child of 3 as it is having value more than 3, 2 is the left child of 3 and 1 is the left child of 2. So all the nodes satisfies the property of binary search tree and the structure remain the same, okay. Our task is to complete the function binary tree to BST, which takes the root of the binary tree as input and returns the root of the binary search tree, okay. The driver code will print the in-order traversal of the converted binary search tree. So basically we are given access to the binary tree through the root of that binary tree, and we will convert it into binary search tree and return the root of the binary search tree. The expected time complexity is n log n and expected auxiliary space is big O of n, and the constraints are number of nodes can go up to 10 to the power 5. So now if we think about solving this problem, then we need to convert a binary tree given into a binary search tree. Okay, so for example, if this is the given binary tree and we want to convert it into binary search tree, now question, it is said that we do not need to change the structure of the binary tree. Okay, so the structure will remain the same, so I have already drawn the structure, right? We just need to manipulate the values such that this follows the conditions of binary search tree. Okay, does it follow the condition of binary search tree? No. Why? There can be many invalidation. One of them is 3 is the right child of 4. In binary search tree, the right child value should be more than the parent child. Okay, and the left child value should be less than the parent child. Okay, but here it does not hold true. So this is not a valid binary search tree. Now we want to convert it into a binary search tree. Now how can we do that? See, understand, there is one property that if we do an in order traversal of a binary search tree, then the values we get will be in the sorted order. Okay, so if we do in order traversal of a binary search tree, then the values which we get will be in sorted order. Okay, now what does that mean? In order traversal means when you visit the left subtree first, then the root node, and then the right subtree first, starting from the root node and recursively. So first of all, you will start traversing from here. Now it has a left subtree, so you will come here. It also has a left subtree, so you will come here. It does not have a left subtree, so this part is over. Now you will note down the root value, so you have finished with the root also. Now you will go into the right subtree. But now this right subtree, for this node again there is a left subtree, so from here will come here. So we will note down this value, then we'll go back, then we'll note down the root value for this subtree. This is the root, this is the left subtree. Then we'll go to the right subtree, then again we'll come here. Okay, after backtracking and so on. So basically we can recursively call first left subtree, then root, and then right subtree. Okay, but on paper, if you want to note down the in order traversal of a binary tree, then what is a general trick? You can first of all draw a boundary across it. So I have drawn a boundary across it. Okay, starting from this, and we will end here, and this is in order traversal. So what we will do is we will mark on the bottom of each and every node. Okay, so here, 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 and here. Okay, and on this path, whenever you encounter the bottom of a node, it means that you have to mark that node. So starting from here, first of all, this node's bottom will be encountered, right? So this is the first node to be visited, this is the second node to be visited in order traversal, this is the third node, this will be the fourth node, this will be the fifth node, this will be the sixth node, this will be the seventh node, this would be the eighth node, this would be the ninth node, and this would be the 10th node. Okay, and this in order traversal of binary search tree should give us what? It should give us values in sorted order. So what I can do is I can simply traverse this binary tree and store all the values in a vector on an array. So I'll do in order traversal of this also. So what I'll get? So I'll mark it. Okay, starting from here, ending from here, and I'll mark the bottom of the nodes. So first of all 7 will come, then 10 will come, then 5 will come, then 6 will come, then 2 will come, then 9 will come, then we will come here 1, then we will go to 4, then we will follow this path, we will get 8, and then we will get 3. So in order traversal of this binary tree will give me these values. So from this, after doing in order traversal, I got the value. Now I will sort these values. So what will I get? I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now I know that when I do in order traversal of binary search tree, I'll get the values in the sorted order. So instead of getting the values, I'll start putting values in the in order traversal. So I'll do in order traversal. This is the first encountered node. I'll keep a pointer I equals to 0. This is the first encountered node. I'll put 1. This is the second encountered node, I'll put 2. I'll keep incrementing I. This is the third encountered node, I'll put 3. Then this is the fourth encountered node, I'll put 4. Here I'll put 5. Here I'll put 6. Here I'll put 7. Here I'll put 8. Here I'll put 9. And here I'll put 10. Why? Because in-order traversal of binary search tree gives me sorted order. Then I can also place these sorted order values in the in-order traversal. I can do the reverse. So I'll get my binary search tree. Now check the condition. For 3, 4 is greater than 3, yes. 2 is less than 3, yes. For 1, all these values on the right side subtree are greater, yes. For 5, all these values are smaller, yes. For 6, all these values are smaller, yes. All these values are greater, yes. For 8, these values are greater in the right side subtree, yes. This is less than that, yes. For 10, 9 is smaller than 10. So this is our binary search tree, okay. So to conclude, what we will do in-order traversal of the binary tree, store the values in an array or vector, sort them and put them according to the in-order traversal in the binary search tree. We do not have to change the structure, and then we'll return the head pointer of the BST. Now let's look at its actual implementation. So if we look at the actual implementation, then what I have done is, this is the function which we are given, and we are given the root of the binary tree. First of all, I have taken a vector v in which I'll store the values of, then I have taken one pointer just to travel. We will see it later. First of all, I have called the function get values in order, passing the root and the vector v. So if we look at this function, what it does is, it takes root and then it takes the vector. I have passed this vector with the help of reference, okay. And first of all, in order traversal, we will traverse the left subtree, then root, and then right subtree. So if root left is not null, then go and do in order traversal in the left part, okay. Then we will note down the current root value. So v dot pushback root data. Then if the right subtree is not null, then go and do in order traversal on the right subtree. So we will get the in order traversal of the original binary tree in vector v, okay. We can also do in order traversal, pre-order traversal, post-order traversal, doesn't matter, because for the first time we just need all the values of the binary tree in our vector v, but we have done in order traversal. Then we will sort those values, okay, and then we will set those values in the in order traversal. So I'll call this function starting with the root, and I have also passed in an index I which is initialized with 0. So in the in-order traversal, whenever the first node would be encountered, index 0 value would be placed. In the second time, index 1 value will be placed, and so on, because we want it in sorted order, okay. And the vector is already sorted. So set values in order, this function is called, will pass the vector, root, and the counter, okay. Again in order traversal, so first left subtree, then current root, and then right subtree. So if left subtree is not null, go and recursively call it. Then set the current node's value. So root data is equals to v of I, okay. V is nothing but the sorted values of the tree, and then we'll increment the counter. So we'll go to the next index for v, and then the right subtree. If root right is not equal to null, set values root right v and I, call that function, okay. So basically we are not changing the structure, just getting the values, sorting them, again doing the in order traversal, and then setting the values back, okay. What would be the time complexity? Time complexity would be n log n. Why? Because this would be the time taken to sort the values. Then you are doing 2 in order traversal, that would take big O of n, but that would not be counted because this is bigger value. What would be the auxiliary space? The auxiliary space required would be how much? Big O of n, because we are taking a vector v in which we will be storing all the n values for the first time, then sorting it, and then again using it back. Now let's submit this code. So let's submit it. So we have solved the question successfully. I hope you have understood the solution completely. Thank you.